2.71. This is the number we call e, the exponential constant, also known as Euler's number or Napier's constant. It's a number that accurately maps out continuous growth and decay, clarifies the natural logarithm, and provides effective tools to evaluate real-world applications. Sounds like a pretty important number, right? Interestingly, mathematicians completely overlooked its significance for thousands of years. Not because they didn't like it, but because they never realized just how essential it was. To adequately appreciate why E is so important, we'll have to dive into some of its history first. The journey begins in the 1600s with a brilliant mathematician named John Napier, who was studying logarithms. If you watched the previous video, you know that Napier's logarithms are different from the ones we use today. Napier did not define his logarithms with bases and exponents. Instead, he used a relationship between two moving particles. We can describe this relationship with this notation. As we mentioned before, Napier did not literally use the natural logarithm, and he didn't use bases and exponents. But as you can see in this notation, Napierian logarithms still relate to natural logarithms. Now, let's clean this up a bit. Take a look at the 10 to the power of 7. At the time of Napier, decimal points were a fairly new idea, so to avoid them, numbers were scaled up. If we unscale Napier's logarithm by dividing by 10 to the power of 7, we are left with the natural log of 10 to the power of 7 over x. Division in a logarithm can be simplified into a subtraction. So this leaves us with a constant minus the natural log of x. Thus we know Napierian logarithms behave very similarly to the natural logarithm. This is just a constant with a natural log. So for now, let's just focus on the natural logarithm. From here, we can come up with a base for Napier's logarithm. To do this, we can use the change of base formula. The Napierian logarithm equals the negative natural log of x. We can rewrite this as the natural log of x over negative 1. This means the natural logarithm of the base must equal negative 1. The natural logarithm is just a logarithm with a base of e. With that knowledge, we can raise both sides as powers of e, and we find that, at its core, Napier's logarithm behaves like a logarithm with a base of 1 over e. Now, technically, we still have the constant, the natural log of 10 to the power of 7. Also, Napier didn't use exponents or bases, so he didn't define his logarithms with a literal base of 1 over e. But from this, we can see that Napierian logarithms are still related to e. Now, Napier constructed huge tables of logarithms, and while e was not specifically mentioned, it was secretly present in each logarithm. Interestingly, in 1618, a table was found in the appendix of Napier's logarithm tables that listed the natural logarithms, even though e wasn't recognized at the time. Natural logarithms, or logarithms with a base of e, continued to astonish mathematicians. In 1647, Greygard de St. Vincent was studying the hyperbolic curve xy equals 1. He found that the area under the curve relates to the natural logarithm. How does that work? Well, let's take a look at the graph of the natural logarithm. If we pick a random x value, we find that the instantaneous slope at that point is 1 over x. In calculus, we call this the derivative. So the derivative of the natural logarithm is 1 over x. 1 over x is just xy equals 1 rearranged. From this, we know the antiderivative of 1 over x, or the inverse of the derivative, is the natural logarithm of x. Knowing the antiderivative allows us to find the area under the curve, or the integral. If we set our lower bound, a, to 1, notice that the natural logarithm of 1 equals 0. Thus, we know that the area under the curve from 1 to any number, b, is equal to the natural logarithm of that number, or the natural logarithm of b. Another mathematician, Christian Huygens, was studying this same curve. Huygens had a very interesting question. What number does b have to be for the area under the curve to equal 1? We know this point as e. The natural logarithm of the exponential constant is 1. Huygens calculated the exponential constant to a whole 17 decimal places, but he thought what he calculated was just another cool number that wasn't very useful. A few years later, the exponential constant was unknowingly developed even more. In 1683, Jacob Bernoulli was exploring a fascinating concept that threw E into the spotlight: compound interest. A bank that offers compound interest increases the balance with a certain percent of your total amount. Each time compound interest occurs, the total amount grows, increasing the amount that will be compounded the next time. Thus, the amount in the account grows exponentially. Bernoulli wondered how the amount of money would behave as interest occurred more frequently, but at lower rates. Let's say you started with $1 in your account. If you receive 100% compound interest yearly, then by the end of the year, you would have $2. But what would happen if you get half of the interest rate, 50%, but receive interest twice a year? Then, by the middle of the year, you would have $1.50, and by the end of the year, you would have $2.25. That's 25 cents more than before. What if we half that again? How much would you earn if you receive 25% interest 4 times a year? Well, then, by the end of the year, you would have $2.44. The pattern continues. The more frequent the compounding, the more money you'd make, even though you get a smaller percentage for each compound interest. Bernoulli found that eventually there was a limit to this. Once we reach 100 or 365, we see that the value per year slows and seems to level out at around $2.71. The more frequent the compound interest, the more the final amount settles and slows down. And if your account is compounded infinitely with an infinitesimally small amount, then by the end of the year, you would have approximately $2.71. And if that number looks familiar, that's because it's E. If we take a look at Bernoulli's discovery, we can model the amount of times the compound interest occurs with the variable n. As n grows larger and larger and approaches infinity, this value approaches E. And if we ignore the dollar sign, we now have a definition for the exponential constant, for Euler's number. But wait, we call it Napier's constant because Napier established logarithms which lay the foundation for the discovery of E. But why do we call it Euler's number? That's because Euler added a significant contribution to the exponential constant and essentially popularized it, discovering a whole host of ways to define E. Euler also found perhaps one of the most amazing properties of E. We've already seen how the exponential constant is related to the natural logarithm, which also has very interesting properties. But the exponential constant has an extremely powerful property that makes it a keystone of calculus: its derivative. Recall that the derivative is a fancy term for the instantaneous rate of change, or the slope at a given point. The slope determines how steep the curve is. And amazingly, if we raise a number as a power of E, the derivative, or the slope at that point, is the exact same as the function value e to the x. This means no matter where you pick on the curve, the slope equals the function value. It's the only exponential function out there with such a property, making it the bedrock for defining exponential growth and decay. Euler's number is a big deal. It is extremely important in calculus, the study of the rate of change. It describes growth itself, holding some of the most fascinating properties in mathematics. It appears everywhere, modeling population growth, thermal cooling, radioactive decay, compound interest, and so much more. Yet for centuries, this powerful number lay hidden in mathematics. A silent reminder that mathematics isn't about memorizing some rules. It's about discovery. And who knows what else may be lying out there, waiting to be found by the next Euler.